All right, so in this video, I'm just going to kind of define what angular size means. So linear size, that's the common way that we measure, the size of something. So, for instance, this building right here, it would be however many feet tall. All right, that's measuring its linear size. All right, and that's a constant. It's always going to be that size. Angular size. Angular size is a way of describing the size of an object uh, based on how far away you are, and kind of how big it looks, depending on where you are. So where this guy is standing, he's supposedly far away from the building. Uh, the building may look big or small to him, all right, depending on the angle from which he sees it. All right, so the further he is back here, the further he is away from it, the smaller the building would look, because the angle right here gets smaller and smaller the further he backs up. All right, or the closer that he gets towards the building, like if he gets, say, right here on the building, right, he still has the same size, but the angle that's created from his point of view. So if he's looking at it, from here, the top of the building to the bottom of the building, well, that's a much larger angle than what it started out as. So the closer that he gets to the building, the bigger this angle is. All right, that is what we call angular size. All right, it's the angle. It's using an angle to describe the size of an object. All right, depending on how far back or forward you are from it. All right. So this all kind of revolves around this S equals R theta formula. So we're still going to be using that, and the way it works, like here I've got, here you are very far away from, I don't know, this might be the little Disney ball, the Epcot Center right here. So if you're very far away from it, you can see the top of the object, and you can also see the bottom of the object right here. Well, we use this angle right here, all right, and we use this S equal R theta formula to kind of make a guesstimate, all right, to kind of describe the size of this. So all the things that we're going to be doing with this angular size is going to be approximations of the size of this object, right? So it's not going to describe its linear size, the distance across the diameter of the object. It's just going to give us an approximation for how big the object is. So, if we have this full circle, all right, and you're supposedly in the middle of it here, this would be one radius of the circle. This would be the other. And so we can use this S equal R theta formula to find the sector length or the arc length of this little swath right here. And that swath, that arc length right there supposedly measures the approximate diameter of that object. So you're kind of you're thinking of the distance that you are from the object as the radius, and the angle that's created between you and its top and bottom is your theta here. All right, and so we use that to measure the diameter of that object. Now, usually, like the context here, it's always objects that are very far away. So this radius here is usually something really big. The distance between you and it are enormous. So the reason we use this is because we don't have a really good way of measuring large objects that are far away. Right? And we kind of the angles that we're using, the thetas, are usually super small. The angle here between the angle that's created between his line of sight and the bottom and top of this building is a really small angle. A lot of times they use this stuff in astronomy to measure, the size of a planet here. So one full sweep here is 6.28, or it's 2 pi. Here on the inside, you can see they're breaking it down into 360s. So from here to the 10 mark would be a 10-degree angle. But then you see these really fine tick marks here. These are each 1 degree. So this would be 1 degree, 2 degree. And they even have it broken down for radians as well. So if this is 1 radian, they have it broken down right here where this would be 1/2 of a radian. All right, and they make smaller and smaller tick marks. Anyway, they're going to be using really, really small angles. That's the idea. All right, we'll do some examples next.